Okay, looking at this, section 5.5, counting techniques. We all know how to count. Why do we need this?
Well, lots of them.
Got lots of numbers. This is in the probability section in the book. How do we get probabilities? If I want the probability of something, it's going to be a fraction, isn't it? Something over something. How do we get those somethings? Right, and you're saying however many. Well, that's counting. So I've got to count things for the top, and I've got to count things for the bottom here. So it's all about counting to get probabilities sometimes. So we're looking at this restaurant, and it says we've got 2 appetizers. We've got how many? 4 entrees. And we've got 2 desserts. Has 2 S's, doesn't it? Okay. Now, just look at the picture. This is in the book, obviously. Just look at the picture. So it's starting out here with the 2 appetizers. And then here's the key. For each appetizer, there's 4 entrees. So those 4 on the bottom are the same as the 4 on top. Then for each entree, there's 2 desserts. So this thing just explodes as it keeps going to the right. So how many different meals could you put together? Well, if you count all these out here on the right-hand side, there's 16. How did they get that if they didn't have a drawing?
Would that be the ands?
Nope, don't even think that right now. Just put that out of your mind for a second. Although I would say to get from here out to this one, what would it be? It would be this particular appetizer, this particular entree, this particular dessert. So that would be an and kind of thing, following that path. And when we look at tree diagrams later on, that's exactly what we're going to do. So you're ahead of your time here.
So, like, are you just trying to figure out how many different possibilities?
Yeah, how many different meals could I get?
Wouldn't that be like, if like if you found out the and thing, would it be like 1 over like 16 seconds? So then you have 16.
If I wanted the probability of getting this meal that I went like that, it'd be 1 out of 16. You're right. But the important thing is, how did we get to 16? They just multiplied. What's 2 times 4 times 2? 16. And so if you didn't see that, that's how they're getting the 16. If I didn't have that drawing at all, if I just told you this part right here, you should be able to figure out, okay, well, there's 16 different meals. Which brings us to this. Now, this multiplication rule is not the this and this. The probability of getting 2 things at once. This says if you've got these different numbers of selections. For instance, let's say Homer has 3 shirts, 4 pairs of shoes, and 5 pairs of pants. How many different outfits could he put together? Now see, he doesn't care about matching anything. How you getting that? Wouldn't it be 60? Because 3 times 4 is 12. 12 times 5 is 60. So I'm just saying, multiply them together. And that's what that multiplication rule of counting is up there. You'd say 3 times 4 times 5. So he could have 60 different outfits. And as you're going through this, notice down here at the bottom, the factorial. I know y'all have seen it. Maybe everybody in this room knows what it means. It just means starting at that number, multiply, counting back. So 5 factorial would be 5 times 4 times 3 times 2 times 1, which I think is 120. It's a short way of saying start at that number and just start multiplying, going back to 1. That's what this is telling you right here. But down there at the bottom, it says 0 factorial equals 1. Why would they do that? And you might not know the answer. We're going to see here in just a second why that might occur. But just remember, by definition, 0 factorial equals 1. Good so far? So everything we're talking about today is about counting. And we need these rules because sometimes it's not very intuitive how to count these things up. All right, let's start with permutations. Just look at this for a minute. It's in the book. So in those formula pages, the chapter 5 section has a lot of stuff in it. Is this formula in there? This one right here? Okay, that's good. What's a permutation? Well, it tells you right here. Here's the number of arrangements of R objects chosen from N objects. Here's what has to be true. Those objects have to be distinct. So I'm looking at all you in the room. You're definitely distinct. Repetition wouldn't be allowed. And the order is important. All right, let's come up with an example. If I were going to line up just those 4 ladies over there. Okay, I've got Clara, I've got Haley, I've got Peyton. So everybody has a different letter there. Okay. How many ways could I line them up at the door? Well, following this formula, it would be what? How many things am I choosing from? 4. So it'd be 4 factorial. What's n? The number I'm choosing from. How many am I choosing at once? A line of 4. Oh man. Is that undefined? It would be if it weren't for this thing back here where it says 0 factorial equals 1. That's why they defined it that way, because sometimes on these formulas you're going to get 0 factorial. So that's 4 factorial, which is what? Equals 4 times 3 times 2 times 1 equals 24. So in other words, for these 4 ladies, I could come up with 24 different lines at the door. And that's just with 4 people. How many could I come up with for all 8 of you? What would change? So it'd be 8 factorial over 8 minus 8 factorial. In other words, just 8 factorial, wouldn't it? Another way of looking at it would be, and this actually comes in handy mark down the blanks. Here's my line. 8 people. How many choices would I have for the first person out of all of y'all? 8. Once that person is in place, how many do I have for the second person? 7. Look what I'm getting. Then 6, 5, 3, 2. And by the time I get to that last place, there's only one person left. Well, isn't that 8 factorial? That's another way of looking at it. And sometimes it's easier, rather than go through the rules and everything, just to figure it out like this. Just draw it out on paper and go, oh, that's 8 factorial. Well, how big is 8 factorial? Let's look at a short way of doing it. I know I could multiply all that stuff out. Let's look at a short way of doing it. Okay. The video of this, the calculator stuff, is not going to show up. Sorry about that. Combination. Look what it's saying. The number of different arrangements of R objects chosen from N. Well, that's just like a permutation, isn't it? The objects are distinct. Yeah. Repetition is not allowed. Yeah. The biggie is the order doesn't matter. If the order matters, it's probably a permutation. If the order doesn't matter, it's probably a combination. They've got a formula down there. Is that in your formula pages? Yeah. And look what else. And both of these, it's putting out here what you put in the calculator. You don't have to remember what to enter in the calculator. This is telling you. Did it do that on permutations? Yep. So here's where the order doesn't matter. Well, there's the formula. Got a question for you. There's 8 of you in here. How many committees of 8 could I have with you 8 folks? How many committees of 8 could I have with you 8? Anybody? I don't think this was showing. This over here with the blue arrow tells you what to put in the calculator. Yeah? Does the order matter in a committee? It's just a group of people. The order doesn't matter. So how many committees of 8 could I get? 1. Right? That's totally different from the permutations. So if in your calculator, I think that might be what Avery did, she put 8, combination, taking 8 at a time, you're going to get 1. Make sure you know the difference in permutations and combinations. Huge difference. Huge. Okay, what if I have, now we got 9 in here now. So what if I have 9 people and I want a committee of 3? Now stop right there. Stop right there. I could start listing, I'm just going to make up letters here for people. So I could have A, B, C. I could have A, B, 8, G at least. See, I could start listing all of them. But it's just a combination, right? It's 9 things taken 3 at a time. What do you get? And then we get to this. Permutations again, but non-distinct items. Okay? And the example I used something like this last period was, let's say we've got 4 green marbles and 6 red ones and 3 blue ones. Now I'm going to line them all up, so it's going to be a permutation. The order matters, but the colors are not distinct. In other words, I've got 4 green marbles. One green marble is just like another green marble. It's not like y'all. Each one of you is unique. So here's the formula for it. And I'm hoping it's in your formula pages. So how many things do I have in all? 13. And then I'm going to say, okay, take the green ones, that'd be 4 factorial, times the red ones, that'd be 6 factorial, times the blue ones, 3 factorial. What do you get? 60,060. It's a 0. Different ways to line those up because they're non-distinct. One green one is not unique from another green one. Now, what if they were different shades of green and different shades of red and different shades of blue? Then what would it be? It'd just be 13 factorial, right? Because it is a permutation. What does that come out to be? Slightly larger than 60,000. So that's what? 6.2 billion again. To recap, we've got permutations when the order matters. We've got combinations when the order doesn't matter. And we've got permutations where the order matters, but the items are not distinct. One's as good as another. It's like cans of soda or something. They're not distinct. This is in the book. Please study it. We're not going to go over this. That'd be silly. But got this out of the book. Notice that this one.
Your calculator's still up.
Okay, thank you. Notice that this one up here, thanks for saying that. And, okay, that one's a combination. This is a permutation. Know when to use each of those. All right, let's work some problems because that's where you really, really learn it. So Dan's going to create a Spotify list with 12 songs. How many ways can the 12 songs be played without repetition? Before you do anything else, stop and say, are we talking about something where the order matters here?
Yes.
Yes. I'm thinking permutation. Are these songs distinct? Yeah. So it's just a plain old permutation, which means it's going to be what? 12 factorial? If you wanted to put it in the calculator, it'd be what? You could either do 12 factorial. Why? Because if you did it out like this, he's got 12 choices for the first song, 11 for the next, 10, and so on. So it's 12 factorial. How big is 12 factorial? Somebody with a calculator help me out.
479,000,001,600. So 479,000,1600.
Thank you. Y'all, think about having 12 songs and listing them in order. Almost 480 million different orders you could come up with. What's the probability of any one order coming up? 1 over that number. We're still talking about probabilities, but we're just talking about the way you get probabilities is counting. All right, license plates. It says how many different license plates can be made using one letter followed by 5 digits. So the way I would do this is draw it out. So I got that, dink, 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 dink. One more digit, right? So here's my letter. Here's a digit, 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 digit. One letter, 5 digits. How many choices of letter do I have? Come on, your alphabet folks. 26? Okay, that wasn't fair. We're talking about the English alphabet. Obviously, some of you were thinking about, another one and didn't come up with 26. All right, so how about the first digit? It says 0 through 9. How many is that? Yeah, 10. Right? That's why our number system is base 10. It has 10 digits. How many for the second digit? Yeah, 10. Can I repeat digits?
Yes.
And then 10, 10, 10. So that's 10 to the 5th power is what? 100,000? Is that right? Yeah. Times 26. What's 26 times 100,000? $20 times 100,000 would be 2 million, right? So 2.6 million? That ought to cover, it wouldn't cover Texas, would it? If that was the scheme. So what do states do? They add more letters and or more digits. So DNA sequences. So we've got, in the DNA chain, we've got A's, C's, G's, T's. What do those stand for? Are they amino acids of some sort? Somebody in A and P, tell me. Let's just assume they are. So are the A's distinct? Is one A as good as another A? Are they all identical? Yeah. C's identical? Yeah. So now what? This is a permutation because we're making a chain. So what's our formula here? But it's not distinct objects. So how many things all together? So we've got 3 A's, 2 C's, 2 G's, 3 T's. So 10. So it's going to be 10 factorial over, and then you just take each one. So this would be 3 A's would be 3 factorial. 2 C's would be 2 factorial. 2 G's would be 2 factorial. And then 3 T's, 3 factorial. What does that equal? You all pop that in your calculator, see what you get, please. Yes, sir. Did you do it the long way or the short way? You put all that in your calculator. Okay, let me suggest, when you've got real little numbers like that, what is 3 factorial? 6. 6. 2 factorial is 2. So 36 times 4 is 144. If you just put 10 factorial divided by 144, you should get the same thing. It worked on this one because the numbers were small. But I'm thinking on a quiz, sometimes every little chunk of time helps. Anybody got a question? Yes, sir.
Can you
I mean, pick a number. 5. 5 factorial means you start at 5 and you work your way down to 1, multiplying. So it's the same as 120. So in your calculator, if you put 5 and then went to math, probability, and choice number 4, I think, you're going to get 120. 10 factorial is 3 million and something. I know just from actually coming up with a softball thing. If you had 10 players on a softball team, how many different ways could you put them out on the field? 10 factorial. So with just 10 people, you'd have 3, well, they're on 9 at a time though. So what if we just had 9 players? How many ways could I put them out there? Because each position is different. $867? How many? How many? Okay, I see your lips moving. What are you saying?
362,880.
About that? I might have misheard a number or something. Is that intuitive? No. With 9 people, there's over 360,000 different ways I could put them out there on the field. And I don't know of a softball team that goes out there with only 9 people. Right? Okay. So what if I did have 10? And we're not going to work it out, but wouldn't it be 10 permutation, 9 taken at a time? Is it? Might be. But we got another person to choose from. Yeah. Okay. This next one, the first time you see a problem like this, the odds are you don't get it. I know that was true in my case. Let's look at it. We got a shipment of 120 components. 4 of them are bad. So here's my suggestion. When you see something starting off like this, write down how many good ones, how many bad ones you've got. So we've got 4 bad ones. How many good ones? 116? Because there's 120 altogether. Okay, just kind of file that away for a second. These you have to read multiple times. So to determine whether the shipment should be accepted, they're going to pull 4 of these at random. If 1 or more is defective, they're going to reject the whole shipment. Does this sound like something somebody would do? Yeah. Yeah, we get a truckload of stuff. I'm not going to examine every single thing if there's a bunch of them in there. But I'm going to pull a sample out and examine that, and I'm going to go, wait a minute. There's bad ones in here. Take it back. Okay. If 1 or more is defective, they're going to reject it. What's the probability the shipment is rejected? This has a lot of stuff going on. Would that be the probability of rejected? Would that be the probability that 1 is bad out of those 4, plus the probability that 2 is bad, plus the probability that 3 is bad, plus the probability that 4 are bad? Technically, that would be it, right? If any of those are true, if this or this or this or this is true, then I'm going to reject it, right? Anybody seeing a way out of this nightmare. Check this out. If one or more. What's another phrase that means one or more? One or more. One or more of you is going to get a lollipop. What does that mean? At least, thank you. So this right here is really saying at least one. If at least one is bad, it's rejected. Now, wait a minute. We've seen that phrase before. It's a shortcut. What's that the opposite of? At least one is the opposite of what?
Probability of none.
None. At least one is the opposite of none. So could I think of it like this? Could I have this probability is 1 minus the probability that none are bad? Would that work? Are these two things the same? Yeah. Y'all with me? That's what I'm saying. The first time you see something like this, it's like, whew. Okay, now I got to just figure out what's the probability that none of them are bad. So the probability that none are bad. Actually, none are bad means 4 good, right? A lot of translating going on here. I got to get a fraction. How am I going to get the numerator? That's going to be how many ways can I get 4 good ones? Out of how many? Here's the trick. 4 out of how many? Good, 116. That's why I want you to write this stuff down out here. So it's 116 things. By the way, does the order matter?
No.
Nope. So it's a combination. I'm pulling 4 out of 116 good ones. That's what you got to get in your head. It's not out of 120 because not all 120 are good. My numerator is how many ways can I get good ones? 4 of them. What's my denominator? 120 chosen 4 at a time. So in your calculator, you're going to put what? 116 combination 4 divided by, and I would use parentheses at least on the denominator, 120 combination 4. What are we going to get? I'm getting 0.8717 rounded off to 4. Yeah, that's the probability of getting 4 good ones. But now I have to subtract that from 1. Need a calculator for that. What am I going to get? 1283. There's our answer. About 13% of the time, that order is going to get rejected, given that situation. How would you like to be the manufacturer of those components? And 13% of the time, they say, take that trainload of stuff back. Or that truckload or whatever. This one, you might want to go back and review the video on. This one's tricky. Gosh, that was so much fun. Let's do another one. Door code. 4 digits. Okay. Here they are. How many codes are possible? Does the order matter? So you're saying the code 1, 2, 3, 4 is the same as 4, 3, 2, 1? The order matters. It's a code to something. So how many choices do I have for the first digit?
4.
Yeah, 10. My little lines are my 4 digits there. And then I can repeat them. So 10,000. 10,000 possible codes with just 4 digits. So the probability, part B, the probability of just guessing it right is what? 1 out of 10,000. Is it possible? Yeah. Likely? No. Here's an interesting one. How many SRSs of size 7 can you get from a population of 100? We started class this semester off saying we're going to sample. We're going to get simple random samples. How many of size 7 could I get from a tiny population of 100? In a sample, does the order matter? No. So it's combination. So I've got 100 things taken 7 at a time. What does that give me? Holy cow. I'm getting about 1.601 times 10 to the 10th. Ten to the 9th is a billion, so this is about 16 billion. That's out of 100 people, y'all. I can get that many samples of 7. Unbelievable. Yes, ma'am.
How did you put that in the calculator to get the combination?
I put this one. Let me show you. Okay, let's see if we can get another one here. Got a couple of minutes. Okay, in the Senate, at least in this problem, 55 Democrats, 45 Republicans. They're going to get a committee of 7. That word committee kind of lets you know probably the order doesn't matter. And they're going to pick 7. So we're going to have 7 on the committee. 45 Republican, 55 Democrats. It helps just to jot that junk down. What's the probability that the committee is composed of all Democrats? Now we're talking probability, so I need a fraction. This is like that component one. How many ways could I draw 7 Democrats out of 55? Does the order matter? No, it's a committee. So it'd be 55 Democrats. I'm not going to put 100 because not all of them are Democrats. So 55 combination 7. There's my numerator. How many ways could I draw 7 people out of the whole Senate? 100 combination 7. Let's see what we get. So only about 1% of the time would that happen just by chance. Look at B. What's the probability that it's all Republicans? What would change? Right? That 55 would go to 45. What's the probability that it's 3 Democrats and 4 Republicans? We're going to quit on this one. Holy cow, what do I have to do? Probability of 3 Democrats, 4 Republicans. How many ways can I get 3 Democrats? That's not it. 55. Chosen 3 at a time. But now for each one of those combinations, I've got a whole bunch of combinations of Republicans, don't I? It's like the menu thing. For each one of these things that's showing, I've got a whole bunch of Republicans that could be there. So this is going to be times, it's the multiply rule here, times 45 Republicans taken 4 at a time. All of that is over, how many ways could I pick 7 out of the Senate? What do we get? I'm getting 0.2442. In other words, a little less than 25% of the time would that happen. Okay. The homework's going to be opened up here in just a little bit. Good luck with these, but you're going to be using the rules we talked about today. It's all about counting.